Welcome to The Explainer. Today we are diving headfirst into something absolutely fascinating, the microscopic combat strategies our medical defenses actually use against pathogens. We're going to compare two incredibly powerful yet fundamentally different tools in our medical arsenal, monoclonal antibodies and traditional antibiotics.
And that brings us to a really core question, right? How do we actually neutralize these microscopic threats? When a virus or a bacteria breaches our body's natural defenses, how do modern therapies step in and stop them? Well, it all basically comes down to two very distinct battle plans.
So here's our roadmap for today. We'll start with those two main strategies of defense, then zoom in on monoclonal antibodies, our precision binders. We'll take a real-world look at the COVID antibody cocktail, shift gears to antibiotics as our machinery inhibitors, and wrap things up with resistance and therapy hurdles.
All right, let's jump right into Section 1, monoclonal antibodies, or as I like to call them, the precision binders.
So what exactly is a monoclonal antibody? Basically, they are identical copies of an antibody that are designed to target one very specific antigen. Think of them like microscopic precision locks, built for a single, highly specific molecular key. Now, while this tech has been in the spotlight a lot recently, it's actually not new at all. Healthcare pros have been effectively using these to treat severe viral infections like Ebola and HIV for a while now. The real secret sauce is that every single monoclonal antibody is crafted to be strictly specific to its exact matching antigen. To actually create these, scientists start by exposing white blood cells to a particular antigen. From there, they carefully single out just one white blood cell, or clone, and that single cell becomes the master blueprint. They produce many identical cells from it, churning out countless exact copies of the antibody. The end result is what's called a hybridoma. It's essentially an immortal factory for that exact antibody, meaning we can scale it up indefinitely to treat thousands and thousands of patients.
So, why is this method such a game changer? First off, it gives us incredible consistency. The exact same quality is maintained across totally different production batches. It's highly reproducible, highly scalable, and makes for really fast, sensitive laboratory assays. But honestly, the most remarkable part? The original antigen doesn't even need to be perfectly pure to get this whole process started, because that meticulous selection step guarantees we find the exact right clones for the specific target anyway.
Okay, moving right along to Section 2, the COVID antibody cocktail. Let's look at a real-world example of this in action.
Let's break down the exact makeup of the Regen-CoV-2 combination antibody cocktail, which you probably remember was authorized for emergency use against COVID-19. It actually contains two distinct human immunoglobulin G1 antibodies, casirivimab and imdivimab. I know, a bit of a mouthful. Structurally, they're both covalent heterotetramers. That basically just means they are made up of four distinct linked parts, specifically two heavy and two light protein chains. We produce these using some pretty sophisticated recombinant DNA technology inside Chinese hamster ovary or CHO cells, and they clock in at nearly identical molecular weights, right around 144 to 145 kilodaltons.
Now in action, these two act literally like guided missiles. Casirivimab and imdivimab bind to non-overlapping parts, or epitopes, of the virus's spike protein receptor binding domain. So by attacking from totally different angles, the combination throws up this incredibly precise physical blockade. It completely stops the virus from attaching to the human ACE2 receptor. It just traps the virus before it could even think about breaking into our cells.
But it gets better. Once they bind, they call in the cavalry, triggering two totally different types of destruction. On one side, we have ADCC, where the antibodies signal human natural killer cells to just seek and destroy the target. On the other side, there's ADCP, where they essentially flag the virus to get swallowed whole and cleared out by human macrophages. It is a brilliant, highly coordinated one-two punch.
All right, let's pivot now to Section 3, antibiotics, the machinery inhibitors.
So, if monoclonal antibodies are an exterior blockade, antibiotics are straight-up internal factory sabotage. Instead of just binding to an exterior target to flag it for the immune system, antibiotics are actually designed to penetrate inside the bacterial cell and start shutting down its critical internal assembly lines. They act way less like handcuffs on the outside and much more like wrenches thrown directly into the gears.
Antibiotics generally use four specific modes of action to pull off this sabotage. They can act directly on the cell wall to compromise its structural integrity. They can inhibit protein synthesis, basically starving the bacteria of the building blocks it desperately needs. They can completely halt DNA synthesis to stop replication in its tracks.
or they can inhibit folate synthesis to cut off a totally crucial metabolic pathway. They are literal targeted inhibitors of microscopic machinery.
Finally, let's look at Section 4, Resistance and Therapy Hurdles, the pushback. Because microscopic combat definitely goes both ways, bacteria actively fight back against these saboteurs, mostly in 3 ways. First, they can chemically alter and deactivate the antibiotic itself. Second, they use efflux pumps. Imagine bailing water out of a sinking boat. They literally just pump the antibiotic molecules right back out of the cell. And third, they can actually modify their own internal machinery, changing the locks so that the antibiotic wrench no longer fits into the gears at all. And this brings us to a really crucial contrast in therapy hurdles. With antibiotics, we're facing active bacterial resistance, pathogens constantly evolving physical defenses, like those efflux pumps, just to survive. But with monoclonal antibodies, the main hurdle is actually a theoretical risk to the patient's own biology. Pumping in external antibodies might attenuate or kind of weaken the body's own natural immune memory response. The worry there is potentially making patients more susceptible to reinfection down the road.
So we're left looking at this fascinating, never-ending arms race. We've seen how monoclonal antibodies act as precision binders that call in cellular reinforcements, and how antibiotics dive deep inside bacteria to sabotage the factory. But whether it's through bacterial efflux pumps or human immune attenuation, there are always massive hurdles. As this microscopic combat continues to evolve, how on earth will medical science stay one step ahead? And honestly, what will the pathogens do next? It's an absolutely incredible battle happening right inside us. Thanks so much for joining me for this explainer, and keep your curiosity sharp.